Welcome back, everybody. In this video, we will be covering the second part of Lecture 13, which will actually split into two sub-videos. The topic is the n-period binomial model. Okay, let's get started. So in the previous video, we learned about the two-period binomial model. However, there's nothing really special about two periods, so we're now going to generalize this model up to n periods, where n is any positive integer. Our setup is going to be as follows. It'll be similar to before. There's a non-dividend paying stock S. The price of this stock today is S0, and the payoff is random and it occurs in the future. The continuously compounded risk-free interest rate is R. It's greater than or equal to 0. And now we're going to have two dates, 0 and capital T, with n equally spaced periods between these dates. So that is, we're going to have two dates, okay, 0, let's do it up here, 0, capital T, but we're now going to have n equally spaced periods between these dates. So in the two-period binomial, we just had one additional period between these dates, which is at date little t. We're now going to have an arbitrarily large number of these periods, say n of these periods. Okay. The first period will be comprised of dates 0 to dates t over n. The second period will be comprised of so here's period P1. The second period, which is period 2, will be comprised of dates t over n to dates t times 2 over n. The third period will be comprised of dates t times 2 over n to dates t times 3 over n, and so forth, all the way until we get to the final period, which will be period n, which will be comprised of dates t times n minus 1 over n to date t equal to t dot n over n. Okay, the length of each period is the same. It's all equally spaced out. So the length of each period is equal to t over n. Okay, and what we're going to assume is that in each period, similar to the two-period binomial model, the economy can either move up or down. If the economy moves up at the period, depending on which state we're already in, the stock price is going to change by a factor of u equal to the gross rate of return. And if the economy moves down, the stock price is going to change by a factor of D equal to 1 over U equal to the gross rate of return. Again, this is going to branch out into a big binomial framework. We can use this model to price any single asset derivative. It's not going to matter. But for simplicity, we're just going to focus on pricing European calls and puts in this lecture with strikes K and maturity of T in their European style. Okay, this slide is a summary, a visual summary of the n-period binomial model. We don't draw a specific end date here because we want to leave it general. We're going to have two dates, 0 and capital T, and we're going to have two basis assets, the stock with a price S0 today and a bond with a price of B0 equal to e to the negative RT. We're going to want to calculate the price of calls and puts that have payoffs at date capital T. These payoffs are going to be a function of the stock price, and the stock price is going to depend on the state of the world. In each period, the economy can either move up or down. If the economy moves up, the stock price changes by a factor of U. If the economy moves down, the stock price changes by a factor of D, and this repeats at each state. Okay, so in the first state, at date 0, okay, at the end of the first period, you can either move up or down. At date t over n, right here in the second period, you can either move up again, uu or ud. If you start in the d state, it's du or dd, and so on and so forth into ad infinitum, right? So there's uuu up here, uud right here. We have udu here, or udd here. Yeah, this is there should be two right there, but you get the point. It's a recombining tree. DDU here and DDD at the bottom, and so forth. Okay. So notice that the number of states is going to increase in each period, which is going to make this a little more difficult than working with our two-period model. Our two-period model had 2 dates at the end of the first period and 4 states at the end of the second period. Okay, this end period model's number of states is going to increase exponentially with the number of periods. Okay, so at the end of the first period, there's 2 possible states, U and D. At the end of the second period, there's 4 possible states, UU, UD, DU, and DD. At the end of the third period, there's 8 possible states. They're not all drawn on there, and so on and so forth, all the way out to n possible periods where there's 2 to the n possible states. This is a lot, but we're going to see, and it's going to be unruly if you wanted to compute all that yourself, even with a computer, if n is very, very large. But we're going to see that we're going to be able to easily simplify this in just 1 second. Okay, so to calculate the call option price or the put option price, what are we going to want to do? We're going to want to use that same logic that we had in the two-period binomial model. We'll essentially have a bunch of stock prices, call, put payoffs out here in risk neutral probabilities all the way at the terminal states. And then we want to go and take the probability weighted average of the call or put payoffs, which depend on the value of the stock in the state, which is influenced by the up or down moves, and discount it back all under the risk neutral measure. Okay, the problem is that to do this, we need to go out, we need to calculate what the stock price is in all these terminal states. We need to calculate what the call price is, or the call payoff, put payoff is, risk neutral probability, and so forth. And if you have a large N in the model, then there's just going to be way too many states to really feasibly do all this computation by hand. Okay. In particular, there's going to be, for example, we'll start with stock prices. There's going to be way too many terminal states if we have a large N to list out all the possible stock prices, which is going to affect the option price, which causes a problem for us, right? So should we just give up on this? No. Luckily, we can use a trick instead. And the trick is to forget that there could be 2 to the n possible states all the way at date to capital T. Forget about that, and instead just think of the model in terms of the number of up and down movements that occur. Okay? In particular, the terminal price of the stock is only actually going to depend on the number of up and down movements that occur. And we're going to be able to write down a quick and easy formula that just takes in the number of up movements, okay, and by extension, it's going to tell us the down movements too. And it's going to output us a price as a function of the number of up movements. We don't need to list out the actual states. Okay, so for example, suppose the stock price moves up I times and down n minus I times by date capital T. Okay, then what we can show, we won't work through it out here, we'll work through a specific example in a second, is that the stock price, okay, is going to be given as follows. We're going to relax the notation that the stock price is dependent on the state and instead say that the stock price at the terminal date is dependent on the number of movements up, I. And this is just going to equal to the gross rate of return U raised to the ith power times the gross rate of return in a down movement to the n minus ith power times the initial stock price S0. For example, you don't really need to know how to get this formula exactly, but it should be intuitive based on our two-period binomial model. But think of just reconciling this with what we've done before. So for example, suppose that we have n equals to 2 or something, and say we have 2 total up movements, then what is the stock price? Okay, at this terminal date. Well, ST of I equal to 2 is just going to be equal to U raised to the squared power times D raised to the N2 minus 2 power times S0, which is just U squared times S0, which is the exact same formula we wrote down for SUU in this two-period binomial model when there were 2 up movements. Okay, so this is just going to generalize everything we had before, but it's going to relax this notation on the state dependence. Okay, we can use this trick. The key trick is that we can forget about all the possible states for which there are 2 to the n, and instead focus on just how many up movements there are in the model. okay, which can range from 0, which would be the state all the way down at the bottom, to n up movements all the way to the top, or n plus 1 possible different ones. Okay, so we can use this same trick to calculate call option payoffs and risk neutral probabilities. Okay, so the terminal payoff of a call or a put option, there's going to be too many states to list out all the payoffs, and the value is going to depend on the stock price. Okay, and so instead what we can do is we can relax the notation on the state again, and instead just use it as a function of the number of up and down movements. Okay, so for example, suppose that the economy moves up I times and down n minus I times. Then what's going to happen is that the stock price from moving up I times and down n minus I times is just going to be u to the I from the last slide times d to the n minus I times S0. Okay, and so the call option payoff in this state, CT of I, or in this certain sequence of events, CT of I, is just going to be equal to the stock price from I up movements, ST of I, just u to the I, d to the n minus I times S0, minus the strike in 0. And equivalently, the put option payoff is just going to be the strike price minus ST of I as well. So all we're doing here is we're getting rid of the state notation, moving it into up movement notations, and saying that the call, the stock price, and the put payoff, okay, are all just functions of the number of up movements in this multi-period economy, okay, in which we can calculate it out via very simple formulas, and it leaves us with only n plus 1 computations instead of 2 to the n. So calculating the stock price and these option payoffs is then straightforward. Once we have these formulas, we can just calculate them all out, no problem, plug them into a computer or Excel. But we run into a little deeper or a little trickier problem when we think about risk neutral probabilities, because we're no longer thinking of probabilities of states, but rather sequences of events of up and down movements. Computing these probabilities turns out to be a little tricky, but if you remember your stats 101 in random variables, it's actually going to be no problem at all, and you're going to see it's very intuitive. Okay, so to do this, what do? So recall in each period that the economy can either move up or down. And the first component that we want to think about when we go back to the two-period model was we wanted to know the risk-neutral probability of a single up movement. This is going to be the cornerstone of figuring out how to calculate the probabilities attached to each of these payoffs here for the FTAP computations. Okay, so first we start by calculating the risk-neutral probability of a single up movement in any single date. The states are all symmetric, or the periods are all symmetric, so the risk-neutral probabilities don't change for a single up movement at each time. And so if you're in a given state, then the risk-neutral probability of moving up over the next period is going to be given as follows. QU equal to our same formula as always, e to the r times t minus d over u minus d, except now the length of time that we use is just cap t over n instead of little t or big capital T we did before. Risk neutral probability of moving down at any point in time is just 1 minus QU. Now QU is a probability of a single up movement in a risk neutral sense. We don't want this particular probability per se. What we want to do is compute the probability of a given number of up movements. So we want to know the probability under, say, measure Q of any number of movements I, which we usually denote as Q of I. Okay. The number of up movements turns out to be something called a binomial random variable, if you think back to Stats 101. Essentially, in each state, we can either move up or down. Okay, and there's n, in each period, we can either move up or down. Okay, and there's n total periods. You can think of this as a Bernoulli trial. Okay, in each period, you can either have success, which is up, or failure, which is down. Okay, or a coin flip. Up is heads, D is down. Okay, so there's n total periods where you can either have success or failure, up or down in each period. And the total number of moves up is just the number of successes or up moves in these n periods or trials. Okay, it turns out that the number I, okay, which is the number of up movements, is just the number of movements or the number of successes in these n periods or trials, where the probability of a single success or a single up movement is given by QU. Okay? This describes, if you think back to Stats 101, a binomial random variable. It was the number of heads, okay, given n coin flips. Okay? And there are well-known probabilities, formulas for the probabilities, mean and variance for these types of random variables. I've written down the formula right here. So for example, think of the risk-neutral probability of moving up, NEI times. This is the probability that a binomial random variable with a probability of a single success equals to QU moves up I times out of n trials. The probability that this happens is denoted capital Q of I. It's equal to n choose I times QU to the I times 1 minus QU to the n minus, excuse me, this should be I right here. Okay, where n choose I, remember from Stats 101, is just n factorial, which is just n times n minus 1 all the way to 1 over I factorial over n minus I factorial. Okay. Think of this concretely. Okay, think of this more concretely. Say, for example, we'll work through, like if you want to compute the probability of moving up I times. So think of the risk-neutral probability of moving up exactly I times in a row to highlight the intuition here. So the probability of moving up exactly I times in a row is just QU times probability of, this is probability of moving up once, times the probability you move up again, QU, times probability you move up again, QU, all the way out to times QU, I times. So this is the probability you move up exactly I times in a row. And let's say the probability of moving down n minus I times in a row after that is equal to QD times QD all the way out to QD. There's n minus I of these. Okay, so for a single draw in which you move up I times in a row and then successively down n minus I times in a row is equal to QU times itself I times, or QU to the ith, times QD to the n minus ith time, which is 1 minus QU to the n minus I. Okay, this is a single path that results in a total of I up movements. It's not the only path. For example, you could move up, you can move down n minus I times, for example, and then up I times exactly in a row and get the same thing. Or you can move up, down, up, down, up, down, and so forth. Okay, you need to then account for the number of combinations or the number of possible ways that you could arrive at such I movements. The way you account for that is you just use this combinatoric thing n choose I. So the probability of moving up I times in a row, not on a single path, but in general, is n choose I, QU to the I, 1 minus QU to the n minus I. For example, suppose we have n equal to 2 and I equal to 2 as well, like we had before. Then how do we compute this probability? Q of I equal to 2 is equal to n, 2 choose 2, choose I, QU to the I squared times 1 minus QU to the 2 minus 2 power. Okay. The combinatoric thing, the n choose I, the binomial coefficient it's called, is going to be n factorial, 2 factorial, okay, times I factorial, 2 factorial, over n minus I factorial. Factorial of 0 is just 1. This is 2 times 1 over 2 times 1 times 1. It's equal to 1. And so this term right here simplifies to 1 times QU squared times 1 minus QU to the 0th power, which is just QU squared, which is equal in that 2-period model to QUU. Okay. So to recap what we have that if we want to use the multi-period binomial model, the number of states becomes unruly at the end, but to calculate the derivative's price, all we need to know is the derivative's payoffs and the risk-neutral probabilities of each of those states. The derivative's payoffs just depend on the stock. Okay, in this particular, the call and put payoffs depend on the stock price at those later dates. You can compute the stock price as a function of the number of up or down movements, st of I equal to u to the I d to the n minus I times S0. You can calculate the call and the put payoffs as a function of the number of up movements I, very straightforward. And you can calculate the risk neutral probability of any number of I up movements via the following formula at the bottom. Qi equal to n choose I, Qu to the I, 1 minus Qu to the n minus I. Once you have that, all you need to do to price the derivative is to plug everything into the fundamental theorem of asset pricing. The FTAP states that the price of any derivative is just its discounted expected payoff under the risk neutral probability measure, or x0 is equal to e to the negative rt, EQ of xt. Okay, remember that the EQ of xt is just a weighted average payoff. Okay, and all you do is you take the probabilities, multiply them by the payoffs across all the states. Okay, we don't use states in this particular example. We're going to instead use the number of up movements, but we're going to have similar computations. There's going to be a total of n plus 1 different possible number of up movements. You start at I equals 0 to n. If you want to price a European call, it's just equal to the FTAP equation, e to the negative r times t, EQ of CT. To calculate EQ of CT, you just take the weighted average payoff. You apply the probability of moving up I times the payoff if it does move up I times across all the possible I's, of which there are n plus 1. So this just becomes a summation from I equals 0 to n of the risk neutral probability of an up movement, of I up movements, Qi, times the call price, or the call payoff in that state, Ct of I. The risk neutral probability is given by the formula n choose I, Qu to the I, 1 minus Qu to the n minus I. The call payoff is given by the max of St of I minus K and 0. And so if you want to get the call price as of date 0, you discount back the risk neutral expected payoff, which is just the sum across all the I's times the call payoff on all the I's. Price of a European put is also similar. You take the sum across all the possible values of the random variable, multiplied by probabilities, times the payoffs, where the payoff is just reversed now. It's put payoff. Whoops, excuse me, this is St of I. Okay. So that's a lot to take in. Let's get a quick little water break in, and we will then use or do 2 practice problems in which we apply this, okay, to 2 problems, and we're going to arrive at the call and put prices. Okay, so I'll give you a little water break and we'll meet back up in a second.